Welcome to another deep dive. Today we're going to be looking at something that's happening all around us all the time, even inside you right now. We're talking about chemical reactions.
Ooh.
It's kind of like unlocking a secret code that explains how the universe works.
Right.
From the simplest things like, ice melting
Yeah.
to the most complex, like
Yeah.
how our bodies function.
Yeah.
It all comes down to chemical reactions.
Absolutely. Chemical reactions are really the foundation of, well, everything.
Yeah.
And once you start to grasp just the basic concepts,
Uh-huh.
you begin to see the world in a whole new way.
Okay, so let's break it down. What is a chemical reaction exactly?
So imagine you have a set of building blocks,
Yeah.
but instead of plastic, these are atoms.
Okay.
In a chemical reaction, those atoms, they rearrange themselves.
Wow.
They break their old connections and they form new ones.
Right.
It's like taking apart a Lego castle and building a spaceship with the same blocks. You still have the same Legos, but you've created something totally different.
So the atoms themselves don't change, just how they're connected.
Exactly. And that change in connection, that creates new substances with their own unique properties. Think about water, for example.
Yeah.
Water is made up of hydrogen and oxygen atoms,
Right.
but when those same atoms are arranged differently,
Yeah.
they can form something completely different,
Okay.
like hydrogen peroxide.
Wow, so it's all about the arrangement.
Yeah.
But how do we actually know when a chemical reaction is happening?
Well,
What are the telltale signs we should be looking for?
there are a few clues you can look for.
Okay.
One is a change in state. Like when water freezes into ice or boils into steam,
Right.
it's still water, but it looks and acts differently
Yeah.
because the arrangement of molecules has changed.
Right. Like how ice takes up more space than water, which is why a full water bottle can crack in the freezer.
Exactly.
So a change in how something looks or feels could mean a chemical reaction is taking place.
Absolutely. Another sign is a change in color.
Okay.
Think about cutting open an apple and watching it turn brown.
Yeah.
That's a chemical reaction with the air.
Hmm.
Or the vibrant colors of fireworks.
Ooh.
That's chemical reactions releasing energy as light.
So it's not just about things changing form, but it's also about new things being created, like those colorful compounds and fireworks. What other clues are there?
Sometimes you'll see a gas being produced.
Okay.
The bubbles in soda are a classic example of a gas escaping
Yeah.
during a chemical reaction.
Yeah.
Or think about baking a cake.
Hmm.
The fluffy texture
Oh.
comes from gas bubbles produced by a chemical reaction in the batter.
So if I see something fizzing, bubbling, or changing color,
Yeah.
chances are there's a chemical reaction going on.
Most likely.
What about temperature changes?
Yes.
Okay.
Heat being released or absorbed, that's another big indicator. Burning wood is a classic example
Right.
of a chemical reaction releasing heat.
Uh-huh.
And a cold pack that you use for an injury
Yeah.
is absorbing heat as a chemical reaction takes place.
So we've got change in state, color, gas production, and temperature change, all fascinating clues that something is happening at that molecular level.
Exactly.
Now, before we move on, let's make sure we've got a really solid definition of a chemical reaction.
Okay.
What would you say is the most concise way to explain it?
A chemical reaction is a process
Uh-huh.
where atoms rearrange themselves,
Right.
breaking and forming bonds to
Yeah.
create new substances with
Yeah.
different properties.
Perfect.
Yeah.
And we can see those changes happening
Yes.
through those telltale signs that we just discussed.
Yeah.
Now, I'm curious, how do scientists keep track of all these atoms and their rearrangements?
Okay.
It seems like it would get pretty complicated.
That's where chemical equations come in.
Okay.
They're a kind of a shorthand way to
Then-
describe these reactions,
Uh-huh.
like a secret code for chemists.
Okay, so it's like a recipe for a reaction.
Yeah, think of it like that.
Tell me more about this chemical code.
Imagine you're baking a cake.
Okay.
You have your ingredients, like flour, sugar, and eggs,
Yeah.
which are like the reactants in a chemical reaction.
Okay.
Then, after mixing and baking,
Yeah.
you get your delicious cake, which is like the product of the reaction.
So a chemical equation tells us what we start with and what we end up with.
Exactly, and it uses symbols and numbers
Okay.
to represent the atoms and molecules involved.
Right.
For example, the chemical equation for water is HO, which means 2 hydrogen atoms are bonded
Right.
to 1 oxygen atom.
So it's a way to write out the recipe in a very compact form. Now, I remember hearing about balancing chemical equations back in school.
Yeah.
Something about making sure the same number of atoms are on both sides.
Right.
Why is that so important?
It's all because of the law of conservation of mass.
Okay.
This law states that matter cannot be created or destroyed. Uh-huh.
in a chemical reaction. We can rearrange the atoms, but we can't magically make more atoms appear or disappear.
So balancing the equation is like making sure we're not cheating by adding extra Legos to our spaceship.
Exactly. And we use coefficients,
Okay.
which are numbers in front of the chemical formulas,
Right.
to balance the equation. Let's say we're burning methane, the main component of natural gas.
Okay.
The chemical equation for that is CH plus OU cohero plus HO.
So that means one molecule of methane reacts with oxygen to produce carbon dioxide and water.
You got it. But notice if you count the atoms on each side, they aren't equal.
Okay.
We have one carbon on each side, which is balanced,
Right.
but there are 4 hydrogen atoms on the left and only 2 on the right. And there are 2 oxygen atoms on the left and 3 on the right. So we need to balance it out by adding coefficients.
Okay, so it's like a puzzle.
Right.
Where we need to adjust the number of each molecule to make sure everything adds up precisely.
Yeah.
And in this case, the balanced equation is CH plus 2 O euros plus 2 HOs.
Okay.
Now we have 1 carbon on each side,
Right.
4 hydrogen atoms on each side, and 4 oxygen atoms on each side. Everything is balanced.
So balancing the equation ensures that the reaction follows the law of conservation of mass.
Yes.
It's like chemical accounting system, making sure nothing is created or destroyed, just rearranged. Before we go any further, let's pause here for a quick question.
Okay.
Imagine you're leaving a bicycle outside in the rain. What signs of a chemical reaction might you observe over time?
That's a great example. You'd probably notice a reddish-brown substance forming on the metal parts of the bicycle, especially if it's made of iron.
Okay.
That substance is rust, and it's a clear sign of a chemical reaction called oxidation,
Right.
where iron reacts with oxygen in the air and water to form iron oxide.
So the formation of rust is a chemical reaction. And that changing color
Yes.
is one of those telltale signs we talked about earlier. Now, I'm curious, are all chemical reactions created equal? Or are there different types of reactions?
You're right. There are different types of chemical reactions, each with its own unique way of rearranging atoms. Shall we explore some of the most common types?
Absolutely. Let's dive into that in the next part of our deep dive.
Welcome back. Before we dig into the different types of chemical reactions, I think it's worth highlighting what we've learned so far.
You're right. We've covered a lot of ground.
We've established that chemical reactions are processes where atoms rearrange themselves, breaking and forming bonds to create new substances with different properties. We also talked about how to identify chemical reactions by looking for clues like changes in state, color, gas production, and temperature.
Right.
And we learned how scientists use chemical equations, like kind of shorthand, to describe these reactions.
Right.
And ensure they obey the law of conservation of mass.
It's like we've learned the basic grammar of chemistry.
Yeah.
Now we're ready to learn some new vocabulary words.
Exactly. Let's start with one of the simplest types of reactions, combination reactions.
Combination reactions.
Yeah.
It sounds like we're combining things.
That's precisely it.
Okay.
In a combination reaction, 2 or more substances combine to form a single, more complex product.
Okay.
It's like taking 2 separate Lego sets and combining them to build one massive structure.
So we're bringing things together to create something new.
Yes.
Can you give us a real-world example?
Think about the formation of rust.
Okay.
When iron reacts with oxygen in the presence of water, they combine to form iron oxide, which is rust. The chemical equation is 4Fe plus 3 hours plus 2 HO or AORs. See how we have multiple reactants on the left side combining to form a single product on the right side?
So that's a combination reaction in action.
Exactly.
We're taking iron, oxygen, and water and combining them to create a new substance, rust.
Precisely.
So if combination reactions bring things together, is there a type of reaction that does the opposite, breaks things apart?
You're on a roll. There certainly is,
Okay.
and it's called a decomposition reaction.
Decomposition.
Yes. It's exactly as you described. A single compound breaks down into 2 or more simpler substances.
Okay.
It's like taking that massive Lego structure we just built and dismantling it back into its original sets or even individual blocks.
That makes sense. It's the reverse of a combination reaction.
Yes.
Do you have an example of a decomposition reaction?
A classic example is the decomposition of water.
Okay.
When we pass an electric current through water, it breaks down into hydrogen gas and oxygen gas. The equation is 2He plus O.
So we're splitting water back into its elemental components.
Yes.
Interesting. So we've got combination,
right,
where things come together, and decomposition, where things break apart. What other types of reactions are there?
Let's talk about displacement reactions. These are a bit more dramatic, like a chemical competition.
Ooh, a competition.
Yes.
I'm intrigued. What's competing?
In a displacement reaction, one element displaces or replaces another element from a compound. It's like one element is more popular and kicks another element out of its spot.
Okay, so it's a battle for who gets to be in the compound.
Exactly.
Can you give us an example of this chemical showdown?
Imagine you have a solution of copper sulfate, which is a beautiful blue color.
Okay.
If you drop a piece of zinc metal into that solution, something interesting happens.
Okay.
The zinc will displace the copper, forming zinc sulfate and leaving copper metal behind.
So the zinc is like the new kid in school who steals copper's date to the prom.
That's a great analogy. The zinc is more reactive than copper, so it's able to kick copper out of the compound and take its place. You'll actually see a reddish-brown coating of copper forming on the zinc.
Oh, wow.
And the blue color of the solution will start to fade.
Okay.
As the copper sulfate is used up. The chemical equation is Zn plus CuSOOSOOS plus Q.
Wow, that's a visual example.
Yeah.
So in this chemical dance, the more reactive element gets to be the partner.
You got it.
Okay.
And this reactivity is a fundamental property of elements influencing how they interact with each other in chemical reactions. It's like a hierarchy of popularity in the chemical world.
Fascinating. So we have combination decomposition and the single displacement where one element takes over. Is there a type of reaction where everyone's switching partners at the same time? Like a square dance of chemicals?
You read my mind.
Okay.
We call those double displacement reactions. They involve an exchange of ions between two reactants. Instead of just one element being displaced, we have two compounds essentially swapping partners.
Okay, I'm picturing it.
Yeah.
Can you paint a picture for us with a real-world example?
Absolutely. One of the most common examples is the reaction between vinegar and baking soda. Vinegar contains acetic acid, and baking soda is sodium bicarbonate.
Okay.
When they mix, the positive and negative ions in the reactants switch places, forming sodium acetate, water, and carbon dioxide gas. That's the fizzing you see.
Right.
The chemical equation is NaHCO plus ChSCO plus ChSCUNA plus HUO plus CoO.
So the sodium from baking soda pairs up with the acetate from vinegar, and the hydrogen from vinegar combines with the bicarbonate to form water and carbon dioxide. That's quite a partner swap.
It is, and double displacement reactions are all around us. They're how we make many important compounds, and they're even involved in the digestion of food in our bodies.
Oh, so we have these four main types of reactions. Combination, decomposition, single displacement, and double displacement.
Right.
It's like learning a new dance for each one. But before we move on, could you give us a quick recap of each type and a concise definition?
Of course.
Okay.
Here's a recap of the four types of chemical reactions we've discussed. Combination reaction. Two or more substances combine to form a single, more complex product. Decomposition reaction. A single compound breaks down into two or more simpler substances. Single displacement reaction. One element displaces or replaces another element from a compound. Double displacement reaction. An exchange of ions takes place between two reactants, forming two new compounds.
That's a helpful summary. Now, I'm wondering, are these the only types of reactions?
Well,
or are there even more complex chemical dances out there?
There are many other types of reactions, but these four are a great starting point.
Okay.
And remember, many real-world reactions involve a combination of these basic types. But there's another fundamental concept that underlies many chemical reactions, and that's what we'll explore next. Oxidation and reduction.
Oxidation and reduction.
Yes.
I've heard those terms before, but I'm not sure I fully understand them. Are we going to need our dancing shoes with this one too?
Maybe not dancing shoes, but definitely your thinking caps. Oxidation and reduction are all about the transfer of electrons. They're like a chemical tug of war with electrons being pulled back and forth.
Okay, this is where it gets really interesting. So it's not just about atoms rearranging.
Right.
It's also about these tiny electrons being transferred between them.
Exactly. And understanding this concept will unlock a deeper level of understanding about how chemical reactions work.
I'm ready to dive in. Lead the way. Welcome back to the final part of our deep dive into the world of chemical reactions.
Oh.
We've explored how atoms rearrange, the different types of reactions, and now we're ready to tackle this electron tug of war.
Right. It's all about oxidation and reduction.
You called it oxidation and reduction.
Yeah.
Okay.
Yeah.
I'm all ears.
Okay.
Break it down for me. What exactly are oxidation and reduction?
At the most basic level, oxidation is the loss of electrons and reduction is the gain of electrons.
Okay.
Think of it this way. If an atom loses electrons, it's like giving away negative charges, becoming more positive. If it gains electrons, it's gaining those negative charges and becoming more negative.
So it's all about these tiny electrons being passed around like hot potatoes.
Yes.
But why are they called oxidation and reduction?
Well, the names are a little bit of a historical quirk. Originally, oxidation referred to reactions involving oxygen because it's so good at grabbing electrons. Think about rust forming.
Right.
That's iron being oxidized as it loses electrons to oxygen.
Ah, so that's why they call it oxidation.
Yeah.
The iron is losing electrons to oxygen. Makes sense. But what about reduction?
Well, reduction initially meant removing oxygen from a compound. But as chemists learned more about electrons, they realized that these oxygen reactions were also about electron transfer. So the definitions were broadened to focus on the gain or loss of electrons, regardless of whether oxygen was involved.
So even though the names come from reactions with oxygen, the core concept is about electron transfer.
Exactly.
Which can happen in many different types of reactions.
And here's the key point. Oxidation and reduction always happen together. It's a two-way street.
Okay.
When one substance loses electrons, is oxidized, another substance must gain those electrons, be reduced. It's kind of like a dance.
Right.
You can't have a leader without a follower.
I like that analogy. It's a chemical tango with electrons as the dance partners.
Yes.
But why should we care about these redox reactions, as you call them?
Well, they're happening inside you right now.
Really?
Respiration, the process of converting food into energy, is a complex series of redox reactions. Glucose from food is oxidized, losing electrons.
Right.
And oxygen we breathe is reduced, gaining those electrons.
Okay.
This electron transfer is what releases the energy our bodies need to function.
Wow. So the very act of breathing and getting energy from food is all thanks to this intricate electron dance.
It is.
Amazing. Are there other examples of redox reactions at work in our daily lives?
Absolutely. Think about batteries.
Okay.
They work by using redox reactions to generate an electrical current. One substance in the battery is oxidized, releasing electrons, which flow through a circuit to another substance that's being reduced.
So those tiny electrons powering our phones and laptops are all thanks to a carefully orchestrated redox reaction inside the battery.
That's right.
That's incredible. But are there any downsides to these reactions? Can they cause problems too?
Yes. Sometimes redox reactions can lead to undesirable outcomes. Corrosion, the gradual deterioration of metals, the classic example. That rusty bike we talked about earlier, that's iron being oxidized by oxygen in the air and moisture forming iron oxide or rust.
So that annoying rust is a redox reaction in action.
Yes.
And it's not just bikes, right? Corrosion affects all sorts of metal objects.
That's right. It's a natural process, but we try to prevent or slow it down by using protective coatings like paint, or by using alloys that are more resistant to corrosion.
It's like we're trying to keep those electron-hungry oxygen molecules away from the metal. Are there other downsides to these redox reactions we should know about?
Another common one is rancidity, a spoilage of fats and oils in food.
Right.
This happens when fats and oils are exposed to oxygen and undergo oxidation, leading to unpleasant tastes and smells. That's why many food products are packaged in airtight containers or have antioxidants added to slow down the process.
So that's why potato chips come in those puffy bags filled with nitrogen gas to keep the oxygen out and prevent those fats from going rancid.
Exactly.
Wow, we've covered so much ground in this deep dive. From atoms rearranging to these electron transfer reactions, it's been an amazing journey into the world of chemistry.
It has.
Thanks for joining us on this incredible journey. We hope you've enjoyed the exploration and learned something new along the way. Until next time, keep those curious minds engaged. And remember, the world is full of wonder if you know where to look.